Instead of just encoding 1 0 in 1 bit, you encode, for example, 9 bits and encode 9 zeros. And if one of these bits flipped, you still have a lot of copies, and you can basically, by majority vote, figure out is it most likely 0 or 1. In quantum mechanics, it's actually not completely obvious whether this idea can apply for multiple reasons. First, you cannot copy quantum information. Number two, in quantum mechanics, if you measure the state, you destroy it. Nevertheless, it turns out that you can use this redundancy to actually encode and protect quantum information, but actually it requires you to prepare these entangled states, these big superpositions that sometimes called Schrödinger cat states. The cat can be alive or dead. So basically, quantum error correction, very counterintuitively, you basically prepare some small cat states to actually protect quantum information. Very counterintuitive. In fact, even theoretically, the fact that it's even possible, it's amazing. They actually, for reasons I just described, it turns out to be very, very hard to do.
This week we spoke with physicist Mikhail Lukin, whose work is pushing the boundaries of quantum computing with arrays of neutral atoms. Lukin explains why building stable superpositions is one of physics' hardest challenges, and how his team is finding clever ways, like error correction and transversal gates, to bring the dream of a scalable quantum computer closer to reality. Please welcome Mikhail Lukin.
The idea of quantum computers in a simple way, which is not entirely accurate, but, it's largely accurate, can be understood as follows. So basically, in a classical computer, all information is represented as sequences of zeros and ones. And in quantum computer, what you do, you replace classical bits by quantum bits, the systems which can be in a superposition state, right, 0 and 1. And the what gives quantum computer is their power is that you can prepare this large superpositions of these quantum registers, right? So you can take a quantum register, and instead of processing just one input, you can process many inputs at once. This is sometimes called quantum parallelism, right? And it gives rise to, all of these famous, examples like Shor's algorithm and things like this. But these big superpositions are actually, it turns out to be very hard to create in a lab. And the reason is somewhat fundamental. So all objects around us, like this table, for example, is in principle made of quantum particles. In principle, in quantum mechanics, this table can be here, in the next office, over at MIT at the same time. But it's never the case, right? Because these large superpositions, they never exist in reality. They all is effectively described, these large objects are described by laws of classical mechanics. So to build a quantum computer, what you need to do, you need to make a large superposition of all of these qubits, and by large, you could say, for example, thousands of qubits. And this is something which does not occur in nature, So the mere idea whether such large superposition can ever be built is not, it has never been done. So it's a very important fundamental question.
Is there a physical limit to how large the superposition can be in neutral atom arrays?
We do not know the answer to this question.
So
we do not know the answer to in any system to this question, but, in neutral atom arrays, we can create now probably by some accounts the largest superposition ever created. And that's why, this is why it's both fundamental and applied, this doing that has a fundamental aspect, but it also has the real world applications.
Like you're describing, because these states don't exist in nature, like these large superposition states, they're very unstable and very hard to produce, right? And that's what everybody's struggling, whatever system they're using. So if you look at transistors, one of the big drivers of the success of transistors is that they were able to create the p-n junction, which maintains a very interesting situation at the microscopic level passively. The p-n junction is passive, so it would be something
because it has nonlinearity, right?
It doesn't. There's basically just the material, just the doping of the material gives you those properties, so you don't have to, for example, externally force them. The question is there a trick like this that has been discovered yet in quantum computing, or is that yet to come? So has anybody found a hack The way that like the PN junction is something like a trick.
So we are finding this as we speak, So okay. So basically, to kind of answer this question, kind of let's, given that we understand the challenge, right? It's kind of useful to go back to mid-90s, where we are now still, And what happened at the time was that there was some early excitement about quantum computers, that people showed that quantum computers can potentially, for example, simulate physical systems much better, much faster than classical computers can do. It was early work by Richard Feynman, and then there was also an important contribution by Seth Lloyd at MIT. And then there was a work by Peter Shor, who showed that quantum computers can solve an important practical problem, factoring, faster than any classical computer, at least any known algorithm in a classical algorithm can do. But at the same time, during this time, like mid to late 90s, there was also very wide skepticism whether quantum computers can be built ever. And the reason is precisely because large quantum objects, can just not be created. And one specific issue there is connected to error rates in quantum operations. So going back to like what I already discussed, in some way, quantum computer can be viewed as a kind of version of an atomic clock. And atomic clocks, as we discussed, are very precise. Atomic clock, can basically, keep the time, or keep the kind of a phase, fixed to like 1 to the, better than power to 10 to the 19, basically. It's an extremely precise, system. But the problem is that in a quantum computer, what you need to do, you basically need to start with, qubits, which you can think about as atomic clocks. But then this, you need to start doing operations on these qubits. You need to basically start doing quantum logic. And, this quantum logic has to be also extremely precise. So, for example, to execute useful algorithm at scale, people believe that you need error rates, something like 1 to the 10 to the 9 or something, 1 in a billion or better.
Sorry, I just have a question. So in clocks, are they actually typically using a single atom, or does it present additional difficulties to go down from a group of atoms to a single atom?
So in clocks, the modern clocks typically use many atoms, but these atoms are not talking to each other. They are completely independent. So you can view them as like just many copies of a single atom, right? And so long as these atoms are isolated, then you can. That's what enables, for example, a new generation of optical atomic clocks. So by the way, you guys might want to someday interview Junier, who will be amazing.
Yeah.
He will be here in February actually for a week. So, but the problem is, if you want to build quantum computer, you really need to make these atoms talk to each other to execute quantum logic. And this quantum logic should be extremely precise, not to the 1 to the not to the 1 in part to the 10 to 19, but 1 to the power to the power 9, right? So, and that is actually like way beyond one could possibly imagine doing kind of at a physical level, precisely because, in contrast to classical like PN junctions, where you have nonlinearity, which can keep you sort of stable at a very high degree. In quantum mechanics, all evolution is fundamentally analog evolution, right? And this kind of, for analog evolution, unless you just let the atoms precess freely, it's very hard to actually, keep it to this kind of accuracy. And so for this reason, in the late 90s, there was a widespread criticism, and actually led by some very famous people in the field, like, for example, Serge Haroche, who got a Nobel Prize in, few years ago. And who really, wrote papers showing that, quantum computers, they call it theory's dream, but experimentalist nightmare. And it should be pointed out that Serge is, someone who actually at the time built largest entangled state. So basically, by doing quantum operations, this kind of with massive superpositions, they are called entangled states. And at the same time, around that time, also people started thinking about something which is called quantum error correction. So and it was, at least theoretically, was supposed to be a solution to this problem. So what is quantum error correction? It's precisely kind of the idea of making this quantum kind of evolution, kind of digital style. It's basically your kind of nonlinearity, if you want, like in a classical system. But what you do, you basically use redundancy. And, you can also have a error correction for classical information, and it's used, for example, for things like information transmission, where instead of just encoding, 1 0 in 1 bit, you encode, for example, 9 bits and encode 9 zeros, And, if you then, let this, state, for example, transmit it or just keep it for a long time, if one of these bits, flipped, you still have a lot of copies, and you can basically, by majority vote, figure out which ones are, is it most likely 0 to begin with or 1. Now, in quantum mechanics, it's actually not completely obvious whether this idea can apply for multiple reasons. First, you cannot copy quantum information. So it's so-called no-cloning theorem is actually a basis for things like quantum communication. So it's a fundamental principle of quantum mechanics, number one. Number two, if typically in quantum mechanics, if you measure the state, you destroy it. So in fact, the reason why large quantum superpositions do not exist can be understood as basically environment measuring. So even the mere fact that someone can actually figure out whether it's stable is here, there, or there, it immediately collapses the state. But nevertheless, it turns out that you can use this redundancy to actually encode and protect quantum information. And the idea there is you basically use entanglement. You delocalize your quantum bit over so-called logical quantum bit now, encoded logical quantum bit. You delocalize over many physical quantum bits. And then what you do, you measure, you don't measure the state completely, but then, once in a while, you measure what's called stabilizers. You basically make a checks. If, for example, like indicating whether, you are still, in the right kind of subspace, and that helps you to kind of, stabilize quantum state. It creates this nonlinearity, similar to classical analogy. And, what the theoretical work by people like Peter Shor, Andrew Steen, John Preskill, earlier Alexei Kitaev, showed, early on that you can, at least in principle, in theory, suppress the quantum errors, using this approach to a very, very high degree. So, but, because, already to begin with, it requires, to have a redundancy, to have several physical qubits to encode even single logical qubit, and actually it requires you to prepare these entangled states. It's basically, in a way, like these big superpositions that are sometimes called Schrödinger cat states. The cat can be alive or dead. Mm-hmm. So basically, quantum error correction, very counterintuitively, you basically prepare some small cat states to actually protect quantum information. Very counterintuitive. In fact, even like theoretically, the fact that it's even possible, it's amazing. They actually, for reasons I just described, it turns out to be very, very hard to do.
Yeah, that's very interesting. Like using the logical qubits to do the quantum error correction.
Exactly.
And so what is now this? I guess it is now like the state of the art in terms of the quantum error. So what is the standard now? And then how do you see it can be moved to the level of 10 to the minus 9 the error rate?
So basically, among the challenges to really make this useful is one, you need, redundancy. You need to have many physical qubits to encode single logical qubit. you also need to have your operations to begin with to be very good. There is something which is called threshold theorem. So basically, if any operation you do introduces more errors than corrects, you're sort of doomed, right? So that's why there is so-called threshold theorem. So basically, physical operations should be very good to take advantage of this nonlinearity to begin with. And then finally, there is something which sometimes is called a control problem. So if you think about your like a cell phone, right? It has a super powerful chip, this chip has, I don't know how many billions of transistors, right? But if you think about how many wires control these transistors, is actually a lot of wires, but not billions, right? And so with these quantum computers in particular, with error-corrected, with this kind of quantum computers based on error-corrected logical qubit, one problem is that if you already start building it with like ingredients where you need to control each physical qubit, in order to control logical qubit, you need to basically have like a lot of wires going on to actually even like just flip one bit or to protect one bit of information, qubit of information. And that actually makes it's a very hard, it's a very challenging control problem. And so for this reason, up to basically, December of last year, kind of state-of-the-art experiments, which were like totally ingenious, extremely, very impressive, controlled, systems of 1 and 2, maybe in one of experiment there was 3 logical qubits, which at most have done, 1 or 2 operations, And so, for example, like Google about a year ago, early last year, they had a paper where we realized, one logical qubit. This logical qubit did not, even do anything. So it's actually they try to keep it alive, and they sort of came just kind of to the break-even point, but it kind of indicates that, the challenge, So in the work which actually, which was just recently published in Nature, so we made some advance to this field. And so what we did, we have basically demonstrated, several kind of like key ingredients of this quantum error correction. One of them was we showed that if we start just with 2 logical qubits, but we increase their size, we could do a quantum logic operation between them such that it improves with the size. And that's a hallmark. So basically by increasing redundancy, we improve the operation, which to begin with is extremely counterintuitive. We create this larger and larger cat state, which should be more and more fragile, but it actually results, we do it in the right way, so it improves the operation. And then in another kind of set of experiments, we have implemented quantum circuits with up to 48 logical qubits. They were small qubits in this case. But nevertheless, we performed algorithms which involved, hundreds of gate operations. Up to now, the record was 2, and we have implemented the algorithm, which is actually complex, which is hard to simulate classically. So, and the key ingredient for that is that, we were able to solve this control problem. And it's actually done by optics. It's kind of, you guys are optics crowd, so you can maybe sort of appreciate it. So in particular, the idea is we use the techniques like special light modulators and acousto-optic deflectors. It's a device which is, I think, similar to what's used in supermarket scanners, barcode scanners. But it turns out to be very powerful because basically there, with one knob, with one voltage, you can address, for example, a set of qubits, which, in the kind of desired way, which includes, a large number, and it's very, very powerful because basically with one control mechanism, we now can control logical qubits rather than physical qubits. So it was a key innovation of this work.
And you use this combination because the AOD, the acousto-optic deflector, has a faster refresh rate than the SLM. Can you also just completely reconfigure the SLM?
Yes, that's it. So this kind of the SLM is, for those who know, is actually an amazing kind of tool by itself. So it's basically a computer-generated hologram where you can basically, with some input, computer input, you can, create an arbitrary light pattern. But it does have one drawback. It's actually slow. And so basically what we do now in the current generation of our experiments, we use a combination of SLMs to create a background static traps. And we use acousto-optic deflectors to actually move traps around. And I should kind of note here that there is another very important ingredient which I did not mention so far. And this is something we already demonstrated almost 2 years ago. In our approach, what we do, we use cold atoms to encode physical qubits. And these atoms are stored in optical tweezers and focused beams of light. And this is good for many reasons. So first, the atoms are extremely well isolated. These atoms are basically atomic clocks, which, other qubit systems are not. And most importantly, once atoms are stored, trapped in these optical tweezers, they can be moved around. And what we demonstrated, about 2 years ago is that actually we can change the connectivity of our processor in real time. So to again step back, typically if you make a processor, right, if the processors which powers your phones and computers, they're designed, and they're fabricated using, optical lithography, UV, lithography. But once it's fabricated, it's fixed. The connectivity, everything was designed at the time when the chip was designed. So what were actually able to show is that by using these atoms and optical tweezers, we can actually reconfigure the architecture. We can change the connectivity in such a way that this, the connectivity, it's itself, like our processor, is like a living organism. And this is enabled now by these acousto-optic deflectors. So we can actually move columns and rows of atoms independently, relatively quickly, in such a way that the way which atoms talk to another atoms, which qubits talk to other qubits, changes in time. And that's the key which allows us now to exercise control over systems, basically looking at logical qubits rather than physical qubits.
At the time you were getting interested in atomic physics and quantum computing, what was the real state of the art? So people were working with systems of cold atoms and trapping them, doing atomic clocks. Like what was really working at the time? Because of course there were no quantum computers at the time.
Yes. So to kind of go back to the origins. So it actually goes back to the point where laser was invented. And when laser was invented, I don't know if you read the history, books, so some people said that laser is a kind of solution looking for an application or something like that. So people
really were looking for a nail.
Yes, people did not quite know. I mean, it was clear that this lasers is a fascinating object that you can produce, very high intensity, directed, coherent light. But it really was not clear, if and how lasers will change the world. And, we now know that, how lasers can change the world in terms of, many areas of human activity. We actually would not be able to, even listen to this broadcast without things like fiber optics, But also very early on, people started to realize that laser is a very special tool for kind of manipulating matter. And one of the very early ideas, which was actually proposed, among others, by Vladlen Litokhov, whose picture one can actually see, but here, so was to basically use lasers, for example, to slow down the atomic motion. And the idea was to use light pressure, and these kind of ideas and kind of eventually, flourished into the fields such as, for example, laser cooling and trapping. So you can use lasers to basically bring atoms to the standstill. You can use lasers to create degenerate atomic gases such as Bose-Einstein condensation. At the same time, people also realized that you can use lasers to build novel type of sensors And in particular, this is how the ideas, of atomic clock came about. And basically the atomic clock uses, light and some radiation, microwave or optical radiation to build, the clocks, which by now, can, skip less than a second during the age of universe. Is actually perhaps the most precise instrument that humankind have ever built to date, So, but actually what all of these kind of directions show you that this field, quantum optics, is kind of very special because it actually combines something which is actually really, fundamental, like cutting edge research, with something which actually is kind of useful for humankind. And to be maximally honest, this is what attracted me to this field to begin with,
But back in 2000s, what were the problems? I recall at that time there was like Nobel Prizes for the BEC, for the Bose-Einstein condensate.
Yes.
Like what people look at that time?
So it goes maybe back even like to kind of early to mid 90s, where, for example, the ideas for this kind of laser, manipulation of atoms have been very well established. And in particular, in 1995, Bose-Einstein condensation has been created of dilute atomic gas. And that by itself has been like an outstanding goal for, a couple of decades. People have been thinking about it. I mean, this Bose-Einstein condensation was also kind of another example of like application, or solution looking for application. People did not quite know what to do with that, but, it enabled a lot of, cool scientific, kind of exploration, studying many body physics, studying, in a very controlled environment. In some way, this work also paved the way to the kind of modern developments, of the type that we will be talking about today, in particular, kind of, for applications in quantum information, in quantum computing. We really utilize, we almost take for granted these kind of techniques, which are actually like completely non-trivial, and some of them, like if you think about it, could you predict that they will work well? This was absolutely impossible, So there was a lot of serendipitous development. There has been a lot of, clever insights, and that's kind of the foundation on which we are building right now.
So what was your first breakthrough in science, which when you studied that, which brought you to the level where you're right now? So what was the pivotal points in your career, or was it maybe some kind of work which changed your direction in science?
I don't know the answer to this question. Maybe it's for historians to judge, but I can tell you that I got interested in the field of quantum information when I was a student, a PhD student in Texas. And during that time, we were working on topics such as lasing without inversion. It's something that you guys might not even remember already, but it was at the time very popular subject, which involved basically designing new types of lasers, which made use of the medium which is prepared in a kind of coherent superposition state. So, as your audience might know, I don't know if you guys talk about lasers,
Of course,
generically, lasers require something which is called population inversion. So basically, more atoms should be in the excited states than in the ground states, for them to stimulate light emission. And that actually makes it actually hard to build certain types of lasers. For example, lasers operating in a short wavelength regime, like UV and X-ray lasers, because population inversion is hard to achieve. And at the time, there was actually a few ideas which people thought about. Maybe you could create a condition such that population inversion is not required. And for that, what you need to do, you need to break the reciprocity between stimulated absorption and stimulated emission. And it is possible to do, it turns out, using, for example, if you start and prepare atom in a coherent superposition state. So this is actually the basis for phenomena such as electromagnetically induced transparency, where the resonant medium can become transparent. And this was a topic of my PhD research, and actually as a part of my PhD, we built the first laser which did not require population inversion. So, and during the time, I also, of course, learned a lot about atomic physics, about also laser physics, about quantum optics. And it was also the time when the first ideas of how to build quantum computers and what to do with them, were emerging. And I've heard about some of these ideas at the conferences, and, actually I got quite excited about, contributing to this frontier. And when I came to Harvard as a postdoc, I had a special fellowship, which I could basically just do whatever kind of I wanted, and this was my idea to start, working in this field. That's how I started working in the field of quantum information.
So what were the first sets of experiments that you carried out after arriving at Harvard?
Going back to, what I discussed before. So basically kind of my entry into this field of quantum information, was kind of from the kind of quantum optics direction, and things like, for example, electromagnetically induced transparency. It's kind of the idea to make the medium transparent at resonance is the kinds of things which, I've explored in my PhD thesis. And one theme which, of kind of my early work and how kind of I arrived to the kind of things which I'm talking about is that actually to begin with, when I went to Texas, I actually really wanted to be a theorist. But and actually I started working on theoretical kind of problems, but then kind of in the middle of the PhD, my thesis advisor, Marlon Scully, came and said, oh, we have all of these theory ideas, no one is listening for us. We need to really do an experiment, and this is actually, and he said, oh, and I have figured it out. So I know that there are now cheap lasers and I have a room with empty optical table and you're in charge, That was my introduction to experimental physics.
How did you feel about that?
Well, I did not feel very good, to be maximally honest, But actually at the end, I was very glad that I had this experience. And actually I ended up during my PhD building, an experiment which was not super complicated, but I kind of built it from scratch. And I think this is kind of an experience which I really encourage everyone, whoever wants to go in experimental physics, do, right?
Does it mean that you were mostly self-taught when you set up this first
Well,
experiment?
I had some advice from some remarkable people, some of whom I still collaborate and work together. So it's hard to be self-taught completely, but yes, I had some moments where I was a little bit, did not quite know what to do. So, and so when I arrived here to Harvard, so together with several of friends and colleagues, and maybe maybe another piece of background. When I arrived here to Harvard, there was no one basically here interested in doing quantum information at this time. And moreover, despite of the fact that quantum optics as a field was invented in the kind of next door, actually right here in the next kind of office, by Roy Glauber, whom you can also see. There was really no one doing. I mean, Roy at the time was already not super young. He was still around. Was fun to talk to, but he was not super active. So there was no one really doing quantum optics either. So, but
what was he known for?
Roy Glauber.
Yeah.
Guys, a young generation, So
I don't know.
So,
they probably know.
I remember the correlation function. Because that's what I was doing during my
Glauber
PhD.
states.
The G2
Glauber states.
I'm not a physicist, so you have to excuse my
I see.
He's
No. Yeah. So Roy, he really, it's kind of, it's interesting. So he invented something which is called, he popularized something which is called sometimes Glauber coherent states, And he has not invented them. It's actually, it was first, Schrödinger appeared in the papers of Schrödinger, they appeared. But Roy really understood that, that there is like a boundary between quantum and classical effects. And he found a way to kind of describe it, in kind of, in terms of correlation functions. And this was really the birth, of quantum optics. I mean, the light around us, it's all emitted by atoms, right? But this light can be described by classical, equations, But at some point, you cannot describe light by classical equations. And Roy introduced a way of thinking, to how this can, how this can be done.
And so it seems like at that time, when you just arrived to Harvard, I understand the community was mostly focused on solving fundamental questions. And then there was a change of trend towards how to use atomic physics for solving like practical problems. So is it true? Like that's because now most of the groups are, or at least it's like a lot of people are focusing on, let's say, quantum computing.
Yeah. I mean, first of all, I kind of disagree with what you imply as your division between fundamental and practical.
Well, it's like observing Bose-Einstein condensate or electromagnetic induced transparency, observing that properties.
At that point, Bose-Einstein condensation was also viewed to be as a tool. And for example, one motivation for developing, for this, exploring Bose condensation was to make atom interferometers.
Mm-hmm.
And atom interferometers are actually practically useful devices. And, in the same spirit, I would not say that, quantum computing is just purely practical problem. I think it's actually a fundamental problem, and in fact, I can explain why it is a fundamental problem. So I think this balance between, pure and kind of basic research and fundamental research in applied physics is, to be honest, is what attracts me to this field.
I have a follow-up question. So, looking at your publications, I see like in 2000, somewhere around 2016, 2017, you very strongly, like your research group entered the field of doing this operations with neutral atoms. So could you maybe tell us a story? What happened at that time?
Okay, so
because people have been working for decades on outer-cooled atoms.
So basically, when I came here, so I was interested to do some work in quantum information. I didn't quite know exactly what to do at it. It was early times where Shor's algorithm was proposed. People started to think about quantum error correction, but it was at the time completely blue sky research. It was very hard to imagine that anyone would ever even start, doing the experiments on this. It was also the time after Chirac and Zoller proposed the first, what I would say, kind of realistic version to build a quantum computer using trapped ions. So, and one of our first contribution to this field was this kind of idea involving the so-called stopped light. You might have also heard about it. So basically, and this idea was based on electromagnetically induced transparency, which actually can be used to slow the light pulses. So it turns out if the light pulse kind of enters the medium, if you can control the group velocity, adjust the group velocity, you can actually slow the light pulse to basically a standstill. We realized that this method can be used as a mechanism to store quantum information, to store a quantum state of light. So the story about how this actually idea emerged is also kind of interesting. So it was it was around the time my advisor Marlon Scully, had a 60th birthday, and somehow there was a kind of a big party. There was a conference in Munich where like a bunch of us was invited, but I could not go because I didn't have visa, but I couldn't come back to the US, and actually so my wife was also a student of Marlon, and so she also could not go. So basically we were we had to think about something to as a kind of present to write some paper for a special issue, And, we really had no idea what to write. And then we thought a little bit about this, kind of stopping light sounds kind of cool, And so we wrote a paper for this kind of obscure, and it like as well, it kind of sounds like an interesting idea. So, and actually that kind of started this research direction on this stoplight. And kind of also early on, like I realized, that one could actually demonstrate this idea using a version of the kind of experiment I built in Texas, And at the time I was actually in the Center for Astrophysics here at Harvard, and another person who was working there was Ron Walsworth. And actually in talking over coffee with Ron, we realized that he has actually most of the tools which we can build this experiment and demonstrate it. And this was like a something which we have done over a couple of months. It's actually like it became like it landed on the front page of New York Times. So, but it was very clear at the time that this kind of operation, this kind of light storage and retrieval, is actually a linear optical operation. So basically, if you want, can use it for memory, but you cannot use it to like process information. So to process information, you needed to kind of introduce some interaction. In this case, between atoms, because in the light storage process, the state of the light, quantum state, is stored in the atomic state, in atomic excitation. And this was kind of the motivation to start thinking about the kind of exciting atoms in so-called Rydberg states. So basically, atoms typically in the natural state is a ground state where electron is rotating very close to the nucleus, But actually, if you excite the atoms to the orbit where electron is far away, it actually, the effective size of the atom increases, and then atoms start talking to each other. And this idea of like exciting atoms to a Rydberg state is a basic idea behind something which is called Rydberg blockade, which actually allows one to, for example, create interactions between stored states in light states stored in the atoms. But it's also the key ingredient behind this kind of recent wave of neutral atom quantum computers. And so this idea, we actually kind of, it dates back to 2000, and we initially started thinking about here at Harvard, but then actually Peter Zoller was visiting. He was at the time already very famous, scientist. And, we went for lunch and we started talking. And then basically I kind of realized that these guys are not only thinking about similar idea, but, they're very advanced, and I was like, oh God, this is famous, scientist, it's like, but then somehow we figured that we're thinking a little bit in a complementary direction. So we decided to join forces. And we had, we wrote two papers, actually one kind of related to light storage and another one related to quantum computing, where we used this idea of Rydberg blockade. So this was 2001. So when I was actually starting my group here in this building in 2001, I thought that this Rydberg, quantum information would be very cool. And I wanted, at the time, I clearly wanted to have my own, at least small experimental lab. But after thinking about this a little bit, I realized that maybe it would be like too challenging at the time to really build an experiment of this type. And the main reason is that to excite atoms in the Rydberg states, you need wavelengths which are much shorter than what's your 632, So basically you need like, blue and UV lasers. And at the time, these lasers simply did not exist. So basically, like, it was sort of clear how one could build it by using, wave mixing and, by using nonlinear optics. But, it was clear that it would be like, 3-4 year project to just build this laser. So that's actually sort of the reason why we did not start working on it in 2001. So had I been more confident, maybe quantum computers would happen much earlier. So, but what happened was that then basically other groups started working on this topic, and then around 2004, Vlad and Vuletic came to MIT, and we started, and actually, after a couple of kind of brainstorming discussion, we started actually experiment here at first here at Harvard, involving kind of these Rydberg atoms more for the purposes of nonlinear optics, not for the quantum computing, but to really create nonlinear interactions between photons. So eventually we moved this experiment to MIT and Vladan's lab, and actually it exists, up to now. And this experiment resulted in a kind of series of measurements where we can show that we could make single photons interact. So, for example, this nice poster, actually I will show you afterwards, is from Australian kid. It was kind of in response to some of this experiment where we showed that we can have like attractive interactions between single photons. People thought it is like similar to lightsabers, and people got very excited. So I got like a kid who said, "Oh, can you send me a lightsaber?" And I'll send you some money back. And his mom wrote some, and he wants some color glue, some,
He specified the
color. Exactly, he specified the color. So, but okay, kind of more to the serious side. So basically, these experiments actually, there, this idea of Rydberg blockade actually worked very well. In parallel, there has been several research groups which have been trying to develop, for example, pursue these quantum computers with the Rydberg atoms. And while there was kind of early on, people showed that one could entangle atoms and one do logic, the problem there was that quality of these logic operations were not very high. So basically, the errors were a little bit, too high. So, and then by 2015, maybe or so, that was a status. So basically, people thought, oh, this Rydberg blockade was a cool idea, but it really doesn't work very well. So there was clear front runners for quantum information are superconducting qubits and trapped ions. When we were talking about this here, we really could not understand what is basically the problem, right? So we decided that we'll build an experiment, small experiment, to try to see whether we can entangle atoms and do, quantum computing and quantum simulations with high fidelities. And we kind of started thinking about it, but it was like basically many people say, well, why do you don't? People have tried it; it does not work. People were really not very encouraging. And then Manuel Anders arrived from Munich. He was actually a postdoc here. And he was planning to work on something completely different. But what happened is, by the time he arrived, we agreed that he comes, and he actually showed up here. He got an offer from Caltech, and he was going to go there. And, I said, look, Manuel, these people say that it's not going to work, but, you have a job, why don't we give it a try? And so basically with Manuel and a couple of, students, and then eventually Hannes Bernian, who's now in Chicago, we kind of started building this programmable atom array. So that was the basis to this kind of 2017 paper where we showed 50 atoms first, and then we extended it to, to larger systems. So we can now control, in our lab over, 500 qubits, and this is not really nowhere near the limit, so that's a basis for all of these developments. Yeah.
You said people were very discouraging. Was that a problem at all to obtain funding?
Yes.
So how did you get it done?
So there is actually, life is a, not straightforward path. So there is always kind of serendipitous, circumstances. And so there is actually a program which is called Vannevar Bush Faculty Fellowship. So it's basically Vannevar Bush was maybe an MIT provost. He was actually quite famous, after the World War II. He was actually kind of an architect of modern funding, U.S. Scientific funding system. And a few years ago, kind of Department of Defense actually started a program which is called Vannevar Bush Faculty Fellowship. So it's basically kind of designed as a program for people who are reasonably established, who have a track record, but maybe they have some kind of wacky idea that they just want to give it a try. And so this was a program together with Harvard MIT Center for Ultra-Cold Atoms, which is also kind of a very special organization, supported this research early on, but this was, so we did not basically ask for funding until, this thing started to work, right? So that's kind of maybe a moral of the story. Yeah.
Yeah, maybe just a question about, so you went over a little bit, I'll just summarize it so before I ask the question. So you have cold atoms and you pull them out individually using laser tweezers and probably with some very precise optics that allow you to focus sufficiently on the single atom. You group them and entangle them into these logical qubits, right? And then, so two questions. One is, you're saying that you actually have to interact with that logical qubit in some way to do the error correction. Physically, what is that interaction? So how do you have this grid, is a 2D or 3D grid of atoms. How do you interact with it in order to do the error correction? And then I have a follow-up question as well.
Yeah, so what you do is you typically have two types of qubits. One, which is so-called data qubits, where the information is preserved. That's one group. And then there is another group, which sometimes are called ancillary qubits. So these ancillary qubits...
And this is a physical qubit or a
These are physical. These are physical qubits.
That's all within one logical qubit.
Yes. Okay. Yeah. So yes, exactly. So this is, to make one logical qubit, generically, you need certain qubits where you store information redundantly, encode it redundantly. Then you use another group of physical qubits, which do these checks. They do these checks to see if the information if errors have been made, basically. And what you need to do, you need to bring this second group. It needs to interact with this first group in a certain way. It's actually quite non-trivial way. It should not be just one-to-one. So typically, one ancillary qubit actually kind of sort of touches multiple, data qubits, and then afterwards you measure these ancillary qubits, and that's what introduces a certain linearity. That's what stabilizes.
Sorry, so when you measure the ancillary qubits, they give you back, in the end, a 1 or a 0, right?
Exactly.
And how does that 1 or 0 do the error correction?
So this gives you a pattern of what's so-called, stabilizers. It basically gives you a pattern of flags.
Okay.
So in a simple way, you could say if no error has occurred, all of these ancillary qubits should be 0. If one of them goes to 1, it's like a flag lights up. It says, the error occurred, and it tells you where it occurred.
And you can then
go and, for example, flip it, or sometimes you can just record that error occurred and keep it, keep track of it, and basically in a software, correct it in a software afterwards.
Okay, that's very interesting.
Yeah.
A follow-up question, just physically, because from watching your talk, I don't remember where you gave this talk, but you show the qubits kind of being overlapping physically. So you're able to move one group over another to create kind of a all-to-all interaction. Don't the traps overlap when you do this? Like the optical traps?
No, we designed this move such a way that traps never overlap. And they come close, but they never touch each other.
What's the requirement? Like how close can the traps come?
So a lot of these things are kind of diffraction limited, so they should be, maybe kind of couple of micrometers from each other, but basically.
But the atoms can interact at that distance.
Atoms
before the trap.
Exactly, because
so that's very lucky, right? That
exactly. That's key. That's a key idea. That's a key innovation of this Rydberg blockade. That's what enables you to. In fact, it enables you, kind of at a very kind of deep technical level. This Rydberg blockade is a process where, by exciting atoms, you basically have two situations. One is when atoms are far away, they basically don't feel each other's presence. But if the atoms are sufficiently close, within the so-called Rydberg blockade radius, which is typically a couple of micrometers, there the interactions to the leading order infinite. So you never can excite more than one atom. And that is actually the way how to make this interaction also being digital, which actually allows us to do, for example, multiple operations in parallel with very little calibration, with very few calibration knobs, And the idea is indeed, so what happens, so basically this movie that what you've seen is a basis for something which is called transversal gate operations. Actually, it turns out to be very efficient way to do operations, quantum operations between logical qubits. Okay, so what you do there is you just take one group of atom, pick it up, bring it such that the atoms sit nearly on the top of each other, but not quite touch each other. Then you just shine one pulse of light, which actually entangles them all in parallel. And then you move back.
Why does one pulse of light entangle them all in parallel?
Because they're all basically positioned properly. They're positioned just to be so so it's kind of very special. And okay, I can explain why this is special. It's special for the following reason. So in these logical qubits,
maybe just so I have a picture in my head, and I think probably everybody has the same question. When you say one pulse of light, is that light hitting all the atoms?
It hits all atoms.
So it's like a spread laser.
Exactly. We actually usually will in fact illuminate them from the side.
Okay.
But so the reason why this so-called transverse, so what I described in technical terms is called transversal gate operation. The reason why this is special is the following. So in logical qubits, quantum information is delocalized over groups of these atoms. So normally, to make quantum gate between them, you have to make, basically you have each atom on the left side or each physical qubit on the left side have to somehow know about what each atom on the right side is doing. And so usually this is like in conventional approaches, for example, something called topological quantum computing, surface code, some of you have heard about it. So what you need to do, you need to somehow, like swap the operation between all of these big chunks of qubits, or in some other way, you can basically need to like take, these excitations in this topological, quantum error correcting always anyons, exotic particles, you need to basically braid, you need to move anyons between, like, from right to left all the way. And this it's a lot of work, right? There's a lot of kind of operations. So basically by doing this,
you're parallelizing.
We parallelize, and actually moreover, when you bring the atoms like on the top of each other and do this gate, what happens is that, if, for example, one of these physical qubits was faulty, right? In doing this gate, it can also affect the other one. But because we don't sort of completely wipe this, one thing around the other, if this guy is faulty, it will produce a fault in a very well-defined place. It turns out to be super useful information in terms of how do you decode the errors. So eventually you measure this ancillas, you figure out, oh, the error occurred here. But in this, if we do this logic gates, quantum gates between logical qubits in this kind of transversal way, it turns out that by actually, measuring these syndromes, by measuring these flags, we actually have a lot of information. Not only that where errors occurred, but also how it propagated. And I think it's a very important insight, which actually will, it's of both fundamental and also very important practical significance.
So maybe one question.
How about this?
To wrap this up.
Yes.
Where do you think the field will be going the next 5 years or the next 10 years? Because there's a lot of hype around.
Yes. I mean, because I do think that's okay. I think we have to be also like very sober about the challenges ahead. So I do think that we are at the start of a new era, where, for example, these ideas of quantum error correction, which have been like super cool theoretical idea, can now be tested in a lab and experimented in a lab. So I would say for our platform, we see a very clear path to experimenting with systems of maybe hundreds of logical qubits, just using the conventional techniques which we already have demonstrated. We need to improve them. We need to make some technical advances in different areas, but nevertheless, I think the path is quite clear. So I would say if we want to go to systems of thousands of logical qubits, and in reality it probably will require, hundreds of thousands of physical qubits, I think some innovation is needed. So, but I'm very optimistic, especially if you kind of look at this problem of building quantum computers, just not being a technological problem, but also a scientific problem. So I think both of these are very important. And I think that's what hopefully our recent work shows, that sometimes by using clever ideas and kind of, really new insights, you can actually circumvent something which could be, frankly, years or maybe decades of work and certainly millions, but maybe billions of dollars.
Yeah, I think that's a great last question, and it's a good moment to stop our discussion. And thank you very much, Misha, for this time, for interesting stories, for clear explanations of this deep and sophisticated topics.
Thank you, guys. It was a lot of fun.